Welcome to Mr. Pratt's Physics. Today we're going to take a look at Kirchoff's laws, Kirchoff's voltage law and Kirchoff's current law, also known as Kirchoff's loop law or loop rule and Kirchoff's node law or node rule. And in a nutshell, what Kirchoff's voltage law, which I'll refer to frequently as KVL, essentially says that if you go around any loop in a circuit, we would find that if you add up all the voltages around the loop, they are going to equal to zero. So if ever you have some battery or something where you have an increase in the electric potential, as you go around the loop, you'll also have some negative changes of potential, some drops across resistors and so on, such that by the time you get back to where you started, of course, you're at the same potential, so you've got the same potential, meaning the sum of all those things was equal to zero. Another way of saying the same thing is that the sum of all the EMFs, where you might say, okay, all these batteries you add up in this loop, that has to add up all to all the IR drops, the voltages across resistors. They have to all be the same. Kirchoff's current law takes a look instead at each node in a circuit, and that says that if I define all the currents as going into the node, the sum of all those currents has to equal zero. In other words, if I've got some of those currents defined going into the node, well, you'll have to have some positive currents and some negative currents. Another way of looking at that is to simply say that going into any node in a circuit, the sum of all the currents going into that node has to equal the sum of all the currents going out of that node, and that is all we mean by Kirchoff's current law. Okay, so let's see this in action. What does that mean practically speaking? We've got this example down here where for that current shown below, the circuit there, let's use Kirchoff's law to find all the loop currents. Let's find the current through the 3 ohm resistor and the voltage from X to Y along here. So by the loop currents we mean, and this is similar to the way that Professor Lewin in the video that you took a look at from MIT defined, taking a look at what's going on around a circuit. We'll pick one point to start at, and therefore I'm going to start at this lower left hand corner here. And then if we go around the loop, and I'll do this in a clockwise direction there, so that my definition of my I1 going around here will be clockwise going around like that. And there's a second loop that we could take a look at here. And when we look at that, I'll also start at the lower left hand corner, and we'll go around the loop in this way. And we'll call that loop current I2, going around clockwise once again. So let's do our analysis. And in the same manner in which Walter Lewin did that, if we start at the lower left-hand corner here again, and now we move upwards toward that battery, we see, okay, the electric potential changes. It's going to increase by 10 volts as it goes from the negative side of that battery to the positive side of that battery. So I'm going to add 10. Now, the current going through this 2 ohm resistor, the current is going through here, which means this electric potential on the left hand side is going to be higher than on the right hand side. So going through that resistor, the electric potential drops by a value of I times R, which is 2 times I1. So I'm going to subtract 2 times I1 over here. Then we come around to this battery here, and we notice that there, once again, we see the minus side first and the plus side second. So that means the electric potential is increasing as we go around the loop in there again. So let me add 5 volts to that. And finally, then we go through this 3 ohm resistor, and the 3 ohm resistor, notice in here we would have I1 as flowing down through there, and so that once again the electric potential would be decreasing there by 3I1. So let me subtract 3I1 here. But notice this resistor also has the loop current I2 flowing through it. And I2, the way we've defined I2, has that flowing upwards through here. And so therefore the electric potential due to I2 would actually be decreasing, or rather increasing, as it goes from the top to bottom. So I need to add 3I2. And then we're back to where we started, and so that has to equal 0. We've gone all the way around the loop. Let me simplify that a little bit. Notice I've got 10 plus 5, so that's 15. I've got minus 2i and minus 3i, so that's minus 5i, 5i1. And then add this 3i2 that we have over here. That has to equal 0, and there's Kirchoff's voltage rule, or voltage law, KVL, around that left-hand loop. Now let's take a look around the right-hand loop. So let me switch colors here, and now we're going to be going around once again also in a clockwise direction. So starting from Y, we start by going through that 3 ohm resistor, but now we're going up through that 3 ohm resistor. So in fact what we're seeing is that according to the loop current I2, we're actually going down in electric potential. So I have negative 3I2. But there's also that I1 loop current, and by the I1 loop current the electric potential would be actually increasing. So therefore I need to add 3I1. Then what we see is we get to the battery, and we notice we're going from the plus side of the battery to the minus side of the battery. So therefore the electric potential is decreasing as it goes through the battery in this direction. So I'm going to subtract 5 volts. And then I get over here to I2, or rather it comes around to the 7 ohm resistor, and the current is going through here, I2 through there, so we see that the electric potential is going to be decreasing as we go through there. So let me subtract my 7I2. And then I'm back where we started, so I've got that has to equal 0. And now I can simplify that a little bit. Let me simplify that by putting the minus 5 out here. And I've got plus 3I1. And then I've got minus 10I2. And that's equal to 0. And we see we end up here, we've got 2 equations in 2 unknowns. So we can easily solve for both I1 and I2 using any method you like. You could use one of those equations to solve for I1, substitute that into the other equation to end up solving for I2, then substitute back to find I1. You could do that the other way around, or something I frequently like to do is I would multiply, for instance, this first equation by 3/5. That way I'd have 3/5 of 15 is 9, 3/5 of 5 is going to be 3, and 3/5 of 3 would be 9/5. Then I would add that equation to the other one, and my I1s would cancel out. I'll solve for I2 and so on. Well, if you end up doing this, what you will find is you'll get values of I2 that comes out actually equal to 0.4878 amps. And I know that's too many significant figures from what we really have, but we're not going to worry about that at this point. We'll also find that I1, solving through this method, ends up giving us a value of 3.2927 amps. And we've used our two equations to find our two unknowns. Those are our two loop currents. Well, what about the current through the 3 ohm resistor? Well, notice the current through the 3 ohm resistor, we have 3.2927 volts, or rather amps, going down, 0.4878 going up, so therefore there's more down than up, so the total current will end up in the downward direction, the way this was drawn, and it will be my 3.2927 minus my 0.4878, and if you do that, you will find that that turns out to be essentially 2.8049 amperes downward, the way the circuit is drawn here. Okay, now we're just left with having to figure out what VXY is. So first, a little bit about convention. What do we mean by VXY? What we mean there is essentially the voltage at node X relative to node Y, so that we can write as Vx minus Vy. So in other words, if the electric potential at X is higher than the electric potential at Y, Vxy will be a positive number. If the electric potential at X is lower than the electrical potential at Y, Vxy will be a negative number. In this case, we'll find that it is indeed actually a positive number. And we can look at this circuit, actually, there are 3 ways we have to calculate what Vxy is, because there are 3 different paths by which we could go from X to Y. One way that we could go from X to Y would be straight from, or actually I'll end up going from Y to X because we're talking relative to Y. So if I kind of call that my 0 and go up to X, we can figure out what that is. So one, we can go take this path, and in that path we'd see, well, what is the voltage gain or loss along this resistor and then through that battery and up to X. We could also do it from this path, because that's another path where I go from Y to X. That would have the same electric potential gain or the same voltage. We could also go this way. So 3 different ways that we could actually solve that. Let's do the easiest way first. Notice if I go over to the right, it's just, well, there's current going through this 7 ohm resistor. So whatever the voltage drop across that 7 ohm resistor, that's going to be the voltage drop from X to Y, so the voltage on X from Vxy. So notice in that case, therefore, what we actually have is Vxy. The electric potential increases as it goes from Y to X through that 7 ohm resistor by 7 times I2. So one way, Vxy is going to be equal to I times R, which is 7 times I2, and I2 we found to be 0.4878, and 7 times 0.4878 comes out to be 3.4146 volts. That's one way we could solve for it. These other 2 ways, well, let's go through this, the left-hand loop. From Y, it increases by 10 volts through the battery, but then it's going to decrease by 2 times I1, so minus 2 times I1 was found to be 3.2927. And you will find that that also ends up being 3.4146. The third way we could do is just go straight through the 3 ohm resistor and the 5-volt battery. Well, through the 3 ohm resistor, there's going to be an increase in electric potential of I times R, where the resistance is 3, and the current is that I3 that we found to be 2.8049. So that goes up some by almost 9 volts, but then it comes down through that 5-volt battery, so minus 5, and you'd find that that comes out to about 3.4147 volts. Okay, we've got more significant figures there than we can realistically handle anyway. Those 3 voltages are exactly the same. So either way, we've got the voltage at VXY is essentially that 3.41 volts. So that is one way of using Kirchoff's voltage law and Kirchoff's current law to solve for us the currents and voltages in a circuit. I'll make another video to take a look at a couple other ways of doing the same thing. You can find the method that is easiest for you to use. In fact, this is not typically the way that I've done it as an electrical engineer, so I'll show you another method in another video.